So we should say from page 2 to 8. It is about image filtering. In this section, we are going to tackle how to blur and sharpen images, applying both several filters and custom-made kernels. Additionally, we will look at some common kernels that we can use to perform other image processing functionalities. OpenCV provides the cv2.filter 2D function in order to apply an arbitrary kernel to an image, convolving the image with the provided kernel. In order to see how this function works, we should first build the kernel that we will use later. In this case, a 5x5 kernel will be used, as shown in the following code. So we create a 5x5 array using NumPy array, and then we set each value to this value. Let's say bring the also techniques. Let me bring it. So I bring documentation of OpenCV. Chapters. Multiple chapters. This is the function. This is the script file. So we have an averaging filtering, kernel average. This is the name of this, and you see it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's 5 by 5, so it's 25 elements. How it is created? It is created because we want that sum of the values be 1. Okay? Before it, let me explain something to you. So filter 2D convolves an image with the kernel. Okay? The function applies an arbitrary linear filter to an image. In place operation is supported, it means that you can put destination, source, so the results will be saved in source src again. Let me explain. Actually, you see, this function does actually compute correlation, not the convolution. that is, the kernel is not mirrored around the anchor point. If you need a real convolution, delete the kernel using flip and set the new anchor to this. So let me explain filtering first. Okay, what is filtering? Special operations are performed directly on the pixels of a given image, and we can classify these operations in three categories. So we want to talk about operations, special operations, are directly are performed directly on the pixels. So we have three types: single pixel operations, neighborhood, geometric transformation. Here we're going to talk about second one. Okay, I reload this page. Maybe the image is shown, so it's not shown. Okay. Let me explain it from somewhere else. Wait a second. Wait a second, okay? As I bring a PowerPoint maybe to explain you the filtering. Okay. So I say it from Gonzalez book. So this is an image. Assume that this is an image. It is the origin. Okay, it's why in our book the horizontal is x, horizontal axis. But anyway, what I want to explain is that we have an image and we have a kernel, another matrix. For example, here is 3 by 3. Okay, it's another matrix, we would put the center of this to each pixel. So we call this W, W00, this one is W minus 1, 0, and so on. And the pixels of the image is called F, okay? Then we multiply corresponding values, okay? Then one value is produced, we put it in the center. We put this in the center. I explain it here again. You see, we have a kernel. F5. Internet is not good enough maybe now. You see, first it's here, then it goes here. At each time, we calculate another value. You see, I refresh it. You see, it's here. A value come here, then a value here, a value here. Okay, a value here, and so on. Okay, so it's what is here. At each location, this value is multiplied by this value to this value to this value to this, okay, and so on. And then we add all of them, we create one value. That one value, for example, for here, it's put here. For example, if they are 1, the kernel values are 1, so the result will be 90, 90, 90, and here these locations are 0, so when we add them and divide by 9, because the number of pixels, the number of coefficients are 9, so we will have 30, okay? No picture, really. If you see the picture, my screen distance, then I think you should see it. Yeah, okay, thank you. So maybe there is a problem in your site, Mustafa Basim Muhammad. Mustafa Bas Muhammad, I don't know. Anyway, this is another example. This is fxy, this is an image, and this is the kernel. We put the center of this 5 here. Then we multiply each coefficient with its corresponding pixel in the image. Then we add them, because all of them are 0, so it will be 0. Then we shift it 1 bit on the right, then 1 bit on the right, and so on. When it reaches here, 9 will be here, okay? This will be here, then the result will be 9. And then if we shift 1 on the right, 8 will be over the 1, then 8 will be multiplied to 1. So the result will be 8, and so on. Okay? So it is called neighboring operation, or convolution, or correlation. There is a difference between correlation and convolution. So what I explained is correlation. So we use a filter, which is a window of a given size, and we travel through the image with this filter by applying the desired operation. Okay. So these words are so we have non-linear spatial filtering. For example, maybe we calculate minimum at each position. I don't know why this pictures doesn't show. Maybe I copy it here in Firefox. Maybe it works. Okay. It's better now. You see, for example, we have a kernel here. The values are shown by A, B, C, D, E, F, G, H, I, and the pixels on the image P1, P2, P3. So we multiply A by P1, B by P2, C by P3, and so on, and then we add them. Then a value is calculated. We put it at location ij. This is the location of ij. Okay, so it is called weighted sum of the image pixels. Uh, so convolution 2D convolution. An image. So images actually are uh, some numbers. Images are that we show. You see, for example, here we show the gray scale, but actually they are some numbers. Okay, so this is the filter. Then we calculate the results and so on. I think maybe you understood something. Okay, so uh, this is the formula of the correlation. It means that at each location we have a kernel, we have the source image. At each location in the source image, we put the center of the kernel. We call it anchor. Okay, it's called anchor. You can select another position in the kernel as the anchor, but normally we select the center of it. We put the center of kernel on each pixel x and y in the image, in the SRC image. Then we calculate the uh, multiplication of the corresponding pixels. Then we add them. Then a value is calculated. That value is put in the destination image at X and Y location. Okay, so SRC is the input image, PSD is the output image. In filter 2D, SRC is the source image. D depth is the desired depth of the destination image. Kernel we should provide, it is the convolution kernel. It should be a single channel floating point matrix. If you want to apply different kernels to different channels, split the image into separate color planes using split and process them individually. So the kernel is a single channel floating point matrix. And also we have border types. When we are at the borders, for the pixels that are at the border, we don't know what we should do. For example, if we put a 3x3 kernel, the center of it here, then part of it will be outside of the image. So we should add some pixels here. We call this padding. For example, we can pad 0. Or another way, it is actually border. At border, what we should do. For example, here we put a value, for example, 0. If these are the pixel values, then we add some specific I, for example, 0. Or we can repeat this pixel value, you see, and here this value is repeated, and so on. So we have some border types. So let me come back here. So this is an averaging kernel. An averaging kernel. You create this by this statement as well. You can do it as well, or you can put these values as well. We have some ones, 5 by 5, so we have 25 ones. We divided by 25 because we want the sum be 1, because it's an averaging kernel. It's an averaging. It's blur an image. Then what we do, we write filter 2D. This is the image, and this is the kernel. What is -1? -1 is the depth of the desired depth of the destination image. I will explain. If we leave it -1, then the type of pixels in the destination image will be same as the original image. So then we apply, so we create the kernel, then we apply the kernel to the source image by applying the aforementioned function as shown in the following code. Now we have seen a way to apply an arbitrary kernel to an image. In the previous example, an averaging kernel was created to smooth the image. So the averaging kernel smoothes the image. There are other ways to perform image smoothing, also known as image blurring, without having to create the kernel. Instead, some other parameters would be provided to the corresponding OpenCV function. In this preview, you can see the full code for this previous example and for next subsection. So let me show you here. If I run this, F5. So this is an image, original image. We smooth the image using a 5 by 5 kernel. What happens? Let me make it bigger. Oh, it's not clear here, but it actually blurred the image somehow. Let me save it this. test smoothing. So here it is show with matplotlib. Here we read the image. Here is the kernel. So here we use filter 2D, one time 5 by 5, one time 10 by 10. So the image is blurred. Oh, oh, sorry, I should delete it because the image is not here. So this is the original image, then it is blurred. Maybe it's here, it's better we can see. You see, it's blurred. It's more blurred than this. It's a version of blurred of this. So it is another type. You see, if you look carefully, you will see that the images are blurred. The images are blurred. Smoothing techniques are commonly used to reduce noise, and additionally, these techniques can also be applied to reduce the pixelated effect in low resolution images. So, one common using of smoothing is reducing noise. When an image has some noise, then we can smooth it to reduce. Of course, it depends also to other parameters, but for the moment, we just say this. These techniques are commented as follows. You can see the output of this script in the following screenshot. So one function is what? Is CV2 filter. Is CV2 filter 2D. But we have also another function. We have blur and box filter to perform an averaging by convolving the image with a kernel, which can be unnormalized in the case of box filter. So let's see box filter. This simply takes the average of all pixels under the kernel area and replace the central element with this average. You can control the kernel size, and the anchor kernel default is -1, meaning that the anchor is located at the kernel center. When the normalized parameter of box filter is true, is equal to true, both functions perform the same operation. In this way, both functions smooth an image using the kernel as shown in the following expression. So a kernel is created. We also have alpha. The size of the kernel we should send to the filter. So let me show you box filter. So we have the layer. We specify 10 by 10. So we want to smooth the image using normalized box filter. So all pixels will be 1. All will be 1. And alpha is the factor that, let me show you box filter. Maybe it's here better. I show you here box filter. So alpha, when normalized is true, it's 1 over this. It means that the number of pixels, number of coefficients in this kernel. So then a normalization is performed. So this box filter below an image using the box filter. Box filter means this filter. Okay. So if normalized is not, will be 1. Okay. So there is no normalization. We also have the so oh, it's the here we wrote normalize equals true. So the values, the coefficients of the kernel 10 by 10 filter are divided by the number of coefficients, which is 100. Okay, and below what below that? Below an image using the normalized box filter. It's always when we use below, it's always normalized. Okay, you see, we provide the size of the kernel, and all coefficients will be divided to the number of coefficients. So the results of this will be same as this, because here normalize is true. When normalize is true, it's equivalent to Belair. When normalized parameter is equal to true, both functions perform the same operation. So in the case of CB2 Belair function, alpha is this. But in the box filter, if normalized is true, alpha is this. But if normalized is false, it is 1. Alpha is 1. In other words, CV2 Belair always uses a normalized box filter as shown in the following code. So these two lines are equivalent. They have equivalent results. But Gaussian filter, Gaussian Belair. OpenCV provides the Gaussian Belair function which Belairs an image by using the following parameters: car size, which is called kernel size, sigma x, a standard deviation in the x direction of the Gaussian kernel, and sigma y, standard deviation in the y direction of the Gaussian kernel. In order to know which kernel has been applied, you can make use of the get Gaussian kernel function. For example, in the following line of the code, Gaussian Belair the image using a Gaussian kernel of size by 9 by 9. So when we want to apply a Gaussian Belair to the image with size by 9 by 9, then we use this. So maybe I also explain to you Gaussian Belair. So Gaussian Belair and image using Gaussian filter. The function converts the source image with a specific Gaussian kernel. In-place filtering is supported. In-place means that for the output you can put the input. It is the operation is performed in place. Sometimes it is supported, sometimes it is not supported for some functions. For Gaussian, in-place filtering is supported. So what is car size? Car size is the Gaussian kernel size. Note that the width and height of car size can differ, but they both must be positive and odd, or they can be zeros and then they are computed from sigma. So we also have sigma x and sigma y. Is if you don't provide cos size, you should provide sigma x at least. If you just provide sigma x, sigma y will be equal to this. But also you can provide both. When you provide sigma x and sigma y, so you see if sigma y is 0, it is said to be equal to sigma x. If both sigmas are 0, they are computed from cos size width and cos size height respectively. Okay. This is one of the best filters, okay, Gaussian. So you see here we put sigma x 0. But what is median function? It blends image with a median kernel as shown in the following. Let me explain the median. Of some. Do you know what is the median of some numbers? Who knows what is the median of some number? It is a non-linear digital technique of noise and image. Large repair. Assume that you have these values. Okay, it's a one-dimensional example. Okay, so the median of these numbers, we sort the number and then this center of it, the middle value is the median. It's here, it's 3. You see? Here, so when we sort them, first we sort them, and then 6, the middle value. Here we sort them, it is 6. Here we sort them, so it is 3. So in two-dimensional also, we have some pixels. We have 9 pixels, for example. If we have a 3 by 3 kernel, then the pixel values of the image under the kernel are sorted and the median of them will be calculated as a result. Okay? So here, for example, it is says median filter image 9. We'll have a 9 by 9 median filter. So you see cos size by cos size. Did you understand median filter? Here, for example, if the kernel is 3 by 3, so these pixels are under the image, neighborhood values. So we put them, we sort them, and the middle one is 1, 2, 4. So the result at its location in the destination image will be this. Okay. As you note that we have two images. Okay. We have one image here. For example, this is SRC. We have an image here. This is the DST. So for example, we have 3, 1, 6, 4, 0, 2, 1, 7, 8, 9, 1, 2, 5. So if the kernel size is 3, so we can add the image, for example, with 0. So because it's 3 by 3, we put the center here. We assume a 3 by 3 neighborhood. So which values we have here? 0. How many 0? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2, 3, 7. What is the median of this? It's this one. So at this location, we put 0 here. Okay? Now we look, for example, here. This is the center pixel now. Okay? So the values that are here, 0, 3, 0. Then we have 1, then 2, then 3, then 6, then 7, then 8. So what is the median? It's 2. So here, the corresponding value here is here. We put 2. Nice. So now we go here. Okay, the center pixel is this. So what is the median of this? 6. 1, 2, 3, 4, the 5 number. No, it's not. Oh, here. No, it's 4, okay? I think it's 4. What do you think? It's not 4? Let me write 0, 0, 0. We have 3, 0. Then we have 1, 4, 6. So it's 4. Then we go here. Okay, we continue. Okay? For example, now look here. So the center pixel is this. So a value for this location. So it's 3, 1. Okay. 1, 2, 3, 1. Then 2, 2. Oh, okay, this is this one, 2, and so on, okay? This is way that median filter is calculated. But it is for median filter, okay? What I explain here, it's for median. I write by mouse. Median filter. It's a non-linear filter. Any question yet? But for the other thing, for the filtering, for example, we have 2, 1, 3, 0, 1, 2, so 1, 6, 7, 8, 0, 1, 1, 2, 3, 4, 5, and so on, okay? We have a kernel like this. For example, averaging 1, 1, 1. So we divide 2, 1 over 9, all the pixels. So it is then about 1 over 9. 1 over 9, what is it? 1 over 9? Maybe I change it there. It is 1, 10, again 1, okay? So the next value will be this, the next value will be this, and all of them will be this, okay? Maybe I don't use this, okay? I use directly this. So what happens, this is the SRC image. We should calculate the destination image. This is DST. We put the center of it here, okay? We put this here. So what is the corresponding of 1 is 2. What is the corresponding of this one is this. What is the corresponding of this is this and this for these two. But what is the corresponding of this? It's outside of the image. We can pad the image with 0. Okay? So when we put 1 here, then the corresponding values of these will be 0. We just have the corresponding values for this one. They are 2, 1, 1, 6. So 2 plus 1, 3, 4, 10. 10 over 9. 10 over 9 will be about 1.1, okay? So at this location here, we put 1.1. Now we put the center of this. Oh, what happened to my computer? Then we put the center of this here. Let me, this, I put it here now. So we multiply corresponding values 1 by 2, 1 by 1, 1 by 3, 1 by 1, 1 by 6, 1 by 7, and these 3 zeros will be multiplied with this 1. So what is the result? 2, 3, 6, 13, 19, 20. 10 divided by 9, 20 divided by 9, it's about 2.2. Then we put the center here. We again calculate. Then here, then here, here, then here. Okay? This is correlation actually. Correlation. Of course, it's you don't have to use equal values. Let me write like this. You can put, for example, 4, 2, 2, 2, 2, and then, for example, 0 is another kernel. So the sum of them is 8 and 4, 12. So I divide all of them by 12. So we can calculate it, okay? We can calculate it. So 2 over 12, it's 1 over 6, okay? It's 1 over 6. It's 4 over 12 is 1 over 6. Oh, sorry. One over 6 and 0. This is our kernel. Now we put it at each location in the source image. At each location. Very well. I draw it with my mouse, so we put the center pixel here at each location. For example, here, what is the value? For example, it is 1, it is 2, it is 20, it is 10. So we put it here, we multiply corresponding values, we calculate the sum of them, then it is the value at this location in destination image. Here, for example, it's here, okay? Then we put the center on the next pixel and do the same. So this is called correlation. If you rotate the kernel 180 and then you put the center of the kernel on each pixel and calculate the multiplication and calculate the sum, then it will be convolution. So the difference of correlation and convolution is this. In convolution, first we rotate the kernel 180 degrees and then we do the calculation. Of course, here it doesn't differ because if you rotate this 180, it doesn't change. Because if it was, for example, 12, then yes, it will be changed because then 12 will be here and 2 will be here. So it will, because it's symmetric, before, of course, before I put this, because it is symmetric, when I rotate it 180 degrees, it doesn't change. But normally, convolution has this difference with correlation. So this is linear filtering actually. When we do convolution or correlation, it is linear. But here, Median filtering is non-linear. It's non-linear filtering. Because here we don't do any multiplication and summation. I hope that you understood something. So we have, when you have the kernel, you use filter 2D to filter the image using correlation, of course. Blur is a version, Blur also does filtering, but it creates the kernel itself. We just should provide the size. It actually uses the averaging filter. Averaging filter means that uh, filters that all coefficients are positive and the sum of them is 1, okay? Box filter also, it is possible that you choose that it is normalized or not. Gaussian blur is another. Gaussian blur is selected from uh, using. For example, we have this image, this original image. If we blur it with Gaussian with a standard deviation of 3, then it is the result. You see, it is blurred in comparison with this. And this is the standard deviation 10. So it has a standard deviation 6. And we have two sigmas, one in X direction and another in Y direction. So maybe I write here 2D. 2D. Of course, it's about so this is 1D, 1 over square 2p sigma e to the power of minus x2 to 2 sigma 2. So we have a parameter here, sigma. Sigma is the standard deviation of the distribution. So we here sometimes we assume that the mean is 0 because also we have a mean. So this is of a Gauss distribution mean 0 and sigma mean. It's here you see this is 0. But also you can have 2D. It is the 2D. Of course, the mean is 0, 0, and sigma in both directions is 1. If you uh, sample it, if you sample a Gaussian, a 2D Gaussian, that it be a kernel, it is, for example, is something like this. The center is big, but when you go to the borders, it is reduces. Okay, I think it's enough. I explained a lot. So median filtering I explained. So the median filtering is used to reduce salt and pepper noise. What is a salt and pepper noise? I explained this one as well. So it is like this. It is like some salt and pepper on the image. We have some white points are added to the image and some black points are added to the image. So that's why we call it salt and pepper noise. It is also known as impulse noise. This noise can be caused by sharp and sudden disturbances in the image signal. It presents itself as a sparsely occurring white and black pixels. An effective noise reduction method for this type is median filter. Okay, it's a median filter. So we have this image. Maybe I make it larger. This is an original image. This is the result of filtering with a median filter with size 1, the kernel 1. This is 3, this is 10. So it's very better than this. Of course, we will learn as okay. Uh, so maybe until here, but I should explain the yeah. It is the original image filtered 2D with a 5 by 5 kernel. These are the smooth. This is 10 by 10 kernel. This is Gaussian blur. This is using box filter. This is using blur. This is using median blur. This is using bilateral filter with small values and bilateral filter with big values. These are what in this script are performed. These operations are in this script. We read the image here. We created some kernels one by hand. We wrote each coefficient. We also can create this with this. Okay, it's commented now. So it has 5 by 5 ones. Then that we normalize the coefficient's value by dividing to 25 because we have 25 1. When we divide them to 25, then these are the results, and the sum of all of these is 1. Also, we can use filter 2D. So we have image and channel averaging 5 by 5, you see, or channel averaging 10 by 10. This is 10 by 10, you see, 10 by 10, but we divide to 100 because the number of ones are 100. So we have two results. We save the results of filtering to these values. Then we use blur. Then we use box filter. What do you mean, Muhammad Hassan? I don't understand you. Let me finish this explaining this, then I will come back to you. We use box filter here. We set normalize to true. The size is 10 by 10. Then we use Gaussian blur. Gaussian blur convolves the source image with a specific Gaussian kernel. This kernel can be controlled using the parameters cos size, sigma x, which is a standard deviation in the x direction of the Gaussian kernel, and sigma y, which is a standard deviation in the y direction of the Gaussian kernel. But when we provide the size and we set the sigma to 0, the sigma X and Y are calculated based on this. I don't want to explain more. This is median value. This is bilateral filter. Bilateral filter. What is bilateral filter? This function can be applied to the input image in order to apply a bilateral filter. This function can be applied to reduce noise while keeping the edge sharp. Normally, when we do a noise reduction using a smoothing, for example, using Gaussian filter, okay, we reduce this noise, but also we reduce the edges of the image. Okay, what is edges in the image? You see, for example, image, these are edges. Then change in the intensity, okay? For example, here from 4 it goes to 152. So we have a big, powerful edge here, okay? Another example, okay? So edges are sudden change in intensity. For example, here we have different. Oh, there is no image here. Okay. See. We have an image here. Then you see, for example, here we see some changes. So it is shown here as white pixels. So the edges are good for finding objects in the image. So if we want to reduce noise, we can use bilateral. Bilateral, of course, has some parameters that maybe, I don't know, I explained them as well or no. Apply the bilateral filter to an image. It has some sigma color, sigma space that I don't want to explain. And D. You just know that we have bilateral filter that reduce noise while keeping edges sharp. So I explain until page 236. Any question? So I think everything is explained here. So what is your question? I am facing a problem when executing some program in Python which contains the word shape. Contains maybe the program objects to this word. So send the program to me now if you can. Send the program to me or copy it here or share, I think, the file. Muhammad Hassan, can you send me your script that I check it, okay? To see files, add new files, share. You can do it here. Okay. I'm waiting for Muhammad Hassan. Muhammad Hassan, please go your program. You can send it by here. File, post file, add new file, share. Okay. When you do it, you upload using this. Muhammad Hassan, do you hear me? Muhammad Hassan? I don't know why he doesn't answer. Muhammad Hassan, please send me your app or Telegram if you can send it here. So maybe I don't know. Muhammad Hassan doesn't hear me. Others hear me or no? Others hear me or no? Okay. Thank you. Last page. What is your question in last page? Ask now. It is by a filter that I didn't explain a lot, okay? I just explained it that it is applied to reduce noise while keeping the edge sharp. Okay, until next session. Goodbye. في أمان الله.